Hi, this is Mrs. Vrobel. This is the beginning of Chapter 10, The Mole. Now, you've probably seen the furry friend that I have in the classroom. He actually has a reason for being there. And you're going to find in this chapter that we're essentially going to do a lot of counting. And with that counting, we're going to do a lot of calculations. So we're going to move between different types of units and use different conversion factors with this chapter. Now, with this chapter, it's really important that we understand what is a mole and how we use it to quantify matter. Sometimes it's a challenge for students because when they hear the term mole, they're not sure if it's a furry animal or it's an actual counting number. We're essentially looking at particles of matter because matter is made up of tiny atoms. There's a lot of them, so we really have to keep track of a very large number, and the mole is a great way for chemists to quantify matter. Now, like I said, it's a counting unit, and I'll just show you some examples of that in a little bit here. It's sort of like a baker's dozen. So you know when you buy donuts or muffins or bagels, you typically buy them in a unit of a dozen. And chemists do something similar to that, but they have very large numbers. So the mole is actually a very large number. Now, in the early part of this chapter, we're essentially going to take moles and we're going to convert it to representative particles. So like I said, it's a very basic counting number. Okay, so since atoms are extremely small, we have a lot of them in a tiny bit of matter. And chemists decided that when they got together, they were going to create an SI unit, and that SI unit is the mole. And essentially, we're using it to calculate the amount of a substance. So if you look at 12 grams of carbon 12, so notice we're talking about just the isotope carbon 12. In that 12 grams, if we were to weigh it out on a laboratory scale, you would find that it amazingly contains 6.02 times 10 to the 23rd atoms. That is a massive number. So as you can tell, the counting gets to be very extreme. And that's why we have to have such a very large unit that we use for counting particles. Now you will see this over and over again from now on. This is essentially Avogadro's number. So there was a chemist early on who quantified the fact that 1 mole of a substance is equal to 6.02 times 10 to the 23rd atoms. Now, conversion factors. When we're looking at moles to particles, so if we want to use that baker's dozen and we want to quantify how much is found in that baker's dozen, we're going to use our conversion factor. So notice that we take Avogadro's number and we put it over 1 mole. In this chapter, it's really, really important that you keep track of units because when you do that, you're going to find that it'll be easier to determine your answer and make sure that you're going in the direction that you need to when you're counting matter. Now, for instance here, we have a problem here. They want to know how many molecules are found in 3.5 moles of sucrose. Sucrose is table sugar, by the way. So we're going to use this conversion factor that I just showed you, and we're going to create a calculation that tells us the molecules in table sugar. So you take your starting number, which is 3.5, and then you just multiply it by a conversion factor. Notice that moles cancel out and you're left with molecules. So we're essentially quantifying matter with Avogadro's number. Now, what if we were given the number of particles and we want to know how many moles that was? So say like we got, I don't know, 1 billion oxygen atoms and we want to know, well, how many moles is that? Once again, you want to use the number that they give you. So how many individual atoms do you have? And notice you're just flipping the conversion factor over. And then when you apply it, so here we have table sugar again, and this person supposedly actually counted all of the molecules within the sucrose. And they essentially used that same conversion factor, they just flipped it. So notice that molecules cancel out and we're left with moles. Okay, let's talk about mass and mole. So the mole is the chemist's baker's dozen, okay? Now when we compare different types of atoms, we need to remember that the mass of 1 mole of one atom has to be different than another. And just to show you this, I counted about 20 marbles, and then I counted about 20 raisins. So notice they occupy a different amount of space, and just by looking at them you can tell that they should have different masses. So please remember, even though they're sharing the same unit of counting, their masses are not going to be the same because one's bigger than the other. So when you look at the periodic table, just remember as you're going from left to right, those masses are increasing. If you're going from top to bottom, those masses are increasing. Okay, now here's the term that we will use a lot in the future here, molar mass. So molar mass, what does that mean? Well, notice it's the mass in grams of 1 mole of a substance. So if I had, like this picture shows you, 1 mole of iron, it should have 6.02 times 10 to the 23rd atoms. No more, no less. Now what we do is, I don't want to say we're doing hand waving here, but we essentially equate that molar mass with the units grams per mole. So you will hear over and over in the future that when we're talking about molar mass, we're talking about grams per mole. Okay, so we're going to take that molar mass that we got from the periodic table and we're going to apply it to moles of copper. Now, what you see at the bottom here, they say 3.00 moles of copper has a mass of 191 grams. Now we're going to see how did they get that. So you're going to take the number of moles that you counted and you're going to multiply it by the mass in grams. Now remember, this is grams per mole, and the mass that you're going to find is actually underneath the element symbol in the periodic table. So that average atomic mass that we were working on way back when, we're going to make that our grams for this equation. So here we take 3 moles of copper and we multiply it by the molar mass of copper. So underneath that element symbol, you should see 63.546 grams of copper. And when you multiply those two numbers together, you get 191 grams of copper. Okay, this is the last diagram for this video, and I want to show you this is really a very good diagram because this helps us to see when we are working between different quantities or calculations. So if we were dealing with mass, so if we were actually weighing something in the lab and we wanted to know moles, or better yet, we wanted to know how much is in that actual mass that we see, we are going to convert between mass to moles to particles. And it's all based on the units that you are using. So if you're going from representative particles to moles to mass, notice that you're going to use Avogadro's number first. So whenever you see a very large number with a exponent on it, good chances we're talking about a representative particle. And notice you would divide by Avogadro's number. So the number should get smaller when you come to moles. And then if you want to convert moles to mass, you need to look at the periodic table for that substance to figure out what is the molar mass for that substance. And notice that you're multiplying by that mass. You're not dividing by it. So that is a really good way to figure out how to go from the number of particles to mass. Now, if you go in the opposite direction, notice that you need to first go to the periodic table and look up the molar mass for that material. And notice it's in the denominator. So you're going to essentially divide by that mass, and that'll give you a smaller number. But then if you want to count the number of particles in that mass, you're essentially going to multiply it by Avogadro's number.